this is from page 5 still. Okay, so 12, Revolution and Intensity Calculus Science. Creating a science expressing the laws of the world in a mathematical form that is independent of any coordinate system, peculiarities, independent of point of view. Again, this is because there are two entities in different universes, and the motion of or acceleration affects the way the other one is perceived. Galileo did it, but Lorentz added the assumption that light waves travel at the same speed in all coordinate systems in constant relative motion. And Einstein refined that theory of special relativity and added a theory where there is also acceleration in the sense of change in direction, not change in speed, called general relativity. According to Einstein, the tensor determines the position of distribution of the object completely. By position, he means four-dimensional space-time of Minkowski. It is more than a vector, since it also indicates how a vector in one system is converted to its associated vector in the other system. A scalar is just a magnitude, like 5, 6, 7. A vector is a scalar with magnitude, plus also has directions, like to the left or right, whatever. And a tensor has both of those, magnitude and direction. Plus, it gives you there's a law of transformation from, if you have a vector here, what it will be in another coordinate system. You have x, y, z here, x, y, z there, you have prime, and a transformation between there, and a vector can span a whole surface, so it gives you the position of the surface. But it could be more than a vector, it could be a matrix, so it could be like a group of vectors. Okay, so in tensors you have you have an addition, you have a law of transformation. Because Einstein used two coordinate systems. In fact, they were moving relative to each other or accelerating even with changing direction, which made it more complicated. According to Einstein, tensor determines the position distribution of the object completely. By position, he means four-dimensional space-time of Minkowski. He added complex imaginary number is square root of -1. Also, so they could put space and time together. It is more than a vector, since it also indicates how a vector in one system is converted to its associated vector in the other system. Really, it is unclear whether what they did is use a constant speed of light, since all observers see it as moving at the same speed independent of their own motion. Hard to believe, but they rely on the stellar operations experiments of Fizeau and the Michelson-Morley experiment, or simply that light moves so fast that it can't be assumed to be the same for all observers, since they move slowly relative to it. Maybe light waves are the same for all of us, since these are electromagnetic waves in the world, Maxwell, and some of these may be replicated in our mind as light. The brain always creates them at the same speed, since the eyes respond to the frequency of light only. That's my theory. Maybe it's because light waves, when they hit our eyes, they hit it with a certain frequency, like the photons or whatever, or light waves hit your eyes. So that generates an electrical signal that goes to your brain. So maybe the speed doesn't matter of the wave. What matters is how frequently they hit your eyes, the retina and cone cells. Einstein created a very complicated field equation of general relativity and equation of motion of general relativity. However, most people know him for his simpler energy equation, and even that only in the case where the object is at rest and has no kinetic energy, E equals mc squared. Einstein also tried to unify general relativity, theory of gravity, with the theory of electromagnetism. The latter has been extended for the theory of the atom by Bohr, Heisenberg, Born, Schrödinger, and Dirac, and others. In a way, by Einstein also. Einstein made contribution to this theory but was against probability, and his theory used the idea of continuous functions, unlike the idea of discrete functions of quantum mechanics. He felt that the latter problem could be settled only if had progress in mathematics so that an exact solution of his field equations was possible. It seems that Sommerfeld and Gödel only gave approximate solutions of these equations. Well, if you look at Einstein's equations, it looks so complicated. But really, I think they're just a system of partial differential equation. Well, that's my specialty in a way. In math, I really like those courses. It's very scary because they're tensors, but really all tensors mean is that it has a special transformation to another coordinate system. But the differential equation is the same. Joseph Fourier had a method called separation of variables. He could solve them analytically by reducing them to ordinary differential equations, which are simpler. In other words, you divide them into several equations where there's only like two variables instead of like four of them. Like you have space is x, y, z, and t. So that's partial because you have many dimensions. But you can reduce it to x and t, and y and t, and z and t. So that would be like an ordinary differential equation with just derivatives from calculus. That would be a differential equation, so advanced calculus. And you can solve those. Although we have methods for solving those, but some of them we can't, so you have to solve by approximation. But Einstein says you need an exact solution for these equations if you want to solve the debate between quantum mechanics and general relativity. So if you know if there's singularities, and if the field equation reduced to quantum numbers, like 4 quantum numbers. First they had 3, then they made 4. Like there also was a debate between Born and Einstein. I think even there was a debate between Max Born and Einstein. Okay, this is page 7. Number 13. The revolution in negative science. A critique of science was setting limits on science. Einstein set limits on the realm of application of the classical mechanics of Newton and electromagnetism of Maxwell. And Heisenberg set a limit on the measurement of position and momentum, so the increased precision in one reduced the precision measurement in the other. So this is Albert Einstein and Werner Heisenberg, etc. I forgot to say before, on Newton, classical mechanics really, they see like Newton as a god, but calculus is very simple compared to, it's brilliant, but compared to the mathematics of today, it's very, very simple. First step, just area and slope. And even if you unify the force of gravity in the heavens and on Earth, very simple because in fact you got it wrong the first time because you used the wrong measurement. But you really have simple equations. I mean, there was no calculus. You even use calculus in equations, just arithmetic or algebra. But you just observe ratios in the cosmos. It's not just an observation, like how to explain the cosmos. I mean, it's very important, but very simple. Calculus was added later, but I don't know, by Laplace or Legendre or Legendre or whatever afterwards, and many other people. And that was before Einstein changed it completely. Number 14, revolution in engineering modeling. Doing research in a virtual laboratory. Testing theories by the design and building of a computer or computer simulation or a mechanical or structural system. Sequential computers, computer algorithms, successful television, airplanes, cars, and industrial machines, etc. Also parallel machines and algorithms like supercomputers and multi-engine airplane. Leonardo da Vinci, Maxwell, Hertz, Volta, Charles Babbage, Thomas A. Edison, Marconi, Alexander Graham Bell, and Alan Turing, Atanasov, Eckert, and Walkley. John von Neumann, Simon Cray, George and Orville Wright, etc. Okay, number 15. Revolution of probabilistic mathematics. This is Pierre-Simon Laplace, Bayes, etc. Okay. This is really imperfect induction since it's based on a sample of one subject only. Determine probabilities a priori or posteriori. For example, in a loaded dice, the outcomes are dependent and not equally likely, so it is very difficult.